I'm just going to do a short spoiler. We're going to talk about frugality. Please don't be frugal with what you eat, because it has been the worst 24 hours in my life since Wednesday. Yeah? I don't know what we eat in the sea, but it has been tough. So, yeah, we live in a world that's fast, connected, and always on. Billions of devices, terabytes, thousands of petabytes, everything moving at full speed in an infrastructure that we can barely see. But there's the thing, all that speed has a cost. This is the world we built for, and when we scale without awareness, energy is spent without purpose, we may run out of power, budget, or even time. And that's what I'm going to talk today. It's how we can make things more efficient with the infrastructure that we deal every single day. So you might have seen this of everything fails all the time. But there are good news. There's laws that help us survive in this chaotic world. And today I'm going to tell you a story about survival, but also about evolution. A couple of years ago, Dr. Werner Vogels, Amazon CTO, brought some simple but powerful laws. This law guy is the frugal architect, someone who doesn't just build for best case scenarios, but also builds for failure, for change, and for survival. So we're going to see a few laws that he brought up. You might see it on reInvent 2023, I think it was the year he sold it out. And it's quite interesting how we're going to approach this whole thing. Usually when we talk about building scalable and distributed system, we usually tend to put the focus on how fast you can recover. You can be prepared, but at some point everything will fail. But that fast recovery, it's also money. How much you invest to really have timeless, to have service, no service downtimes. Huh? Usually, when you get into conversations with CTOs, CIOs, or the financial officer, they always come to say, hey, they're not just asking for cost reduction, which you will start seeing more and more in those conversations. They want modernization, performance, and elasticity all at once. It's kind of a joke, like trying to juggle with balls and seeing what's the best approach and trade-off, and we'll talk about that during this session now. And this brings us to the first law. It's make cost a non-functional requirement. We always think about scalability, resiliency, availability, security, but how often do we design with cost in mind? You got it? So cost isn't just an operational concern, it's an architectural decision. And from the first line of code up to the last production instance that you put in your environments, every choice you make affects how much your system costs to run. And beyond all that money, when we reduce waste, we also reduce our carbon footprint. And I think there's a huge pressure on many companies to try to be more efficient and sustainable. So getting this principle of how we put cost as a core design principle, let's put this in practice. This is a simple application with a Monte Carlo simulation. We will use K6 from Grafana to do some load testing. And we'll use KEDA, Kubernetes Event-Driven Architecture, because rather than looking after CPU and memory, I would like to look after latency, because customers doesn't care how busy is your server. They really care about the user experience, how fast your application will respond. It will take the metrics from Prometheus, and it will, at some point when it reads, will say, oops, I need to scale up or down. Depends on how that latency will hit our application. But we also have Carpenter, which is an open source orchestration that will look after the unscheduled pods and will just be ready to automatically provision infrastructure on our behalf. Huh? So, steps of how we're going to do it. I'm going to start with an x86 deployment. It's on demand, which is pay as you go. We'll see how it works on the Monte Carlo simulation when we load test the replicas, and I'll show now in the screen, you will see the cost of how much is running the whole thing. And then we'll evolve this architecture in 2 steps. Second step will be moving to ARM architectures. In our case, it's Graviton chips. It's AWS Silicon. Not sure if you heard that before. I have one chip here if later you want to see it. Rare to see it out of Amazon's events. Well, we brought it there. The theory says that Graviton is faster, better price performance, and energy saving compared to x86 architectures. And we'll see if that's true or not. And then in a second step, we'll move to Spot. Spot is the spare capacity we have in the data centers. It's kind of picking a business class flight very, very cheap. You might get even 90% of discount. The only trade-off is that AWS can ask for that, reclaim it with 2 minutes in advance. But if your workload is flexible and resilient, you can save big. And we'll see how that works. From an application perspective, same app, same logic, no code changes. But with each step, we'll make it smarter infrastructure decisions to reduce the cost and improve the performance. I put this with different panels. You will see on the top is the EKS node viewer. It shows all the nodes currently running in our cluster, the type, the architecture, if it's x86 or ARM, and the capacity. This is what Carpenter will manage to provision. Then in the middle one, we see how many replicas are running. We have right now a Monte Carlo deployment. And this is where Keda will scale based on user perceived latency, those 500 milliseconds, rather than CPU and stuff like that. And then right now, one replica, we'll see how much it's able to scale on that side. And then on the bottom left side, you will see the actual instance, the CPU and memory usage of those nodes running in the simulation. And the idea here is that you might see that CPU usage might or not might affect the performance. It's not always that having large CPU, you have better, or you have worse performance in this case. Also, a single point on the architecture. x86 usually runs on multi-thread or SMT. What you have in ARM architectures is a single core. So you have full potential for what you want to run on your side. And then on the bottom right is just watching how the pods come live and disappear as we try and test the whole thing. So now that we've seen our cluster layout, let's put some traffic. We've written 3 different scripts, one for each scenario. For the first one, it's just a quick validation on x86, but then we'll have another one to compare, that's kind of the baseline, to compare x86 with Graviton, and we package this script to have it there. So if I get into the pods, you will see that there are some currently running and coming live. But just in case, we'll take a peek at the logs to make sure that everything is working. So we'll see if the load test is active. We just run it there. It's coming up 4%. You see we have 100 virtual users, and the test will take like 7 minutes, but I speed the video because the conference was asking for shorter talks. So we had to do some tricks there. So we have, you see here, it's getting, so let's start with the test. It's already running. Keep an eye on the latency. It's right now 39 milliseconds, but I spin up so you can see that how bypass, and you will see how Carpenter starts adding more nodes on the top. Look at the price and the cost per hour, but also the total that you have on top of that. So it's currently provisioning, and so far we have 5 replicas already. As it puts more nodes, it will decrease the latency, so we'll try to optimize those latency and remove nodes to keep it all there. And that's what I was telling about CPU. You have 48 to 1%. Doesn't mean that you're hitting that kind of performance. And you see pods coming live. It will come up and down all the time as it scales. So we have Carpenter working like a harm, putting more nodes and stuff like that. But see that everything he's putting is on x86 on demand. And it comes up with 2 nodes to have the whole situation. 9 replicas, it dropped to 5. And that's kind of the scenario where we're coming from. Huh? So this is kind of when it finished the 7 minutes test. Our load test is done, and here's kind of a snapshot of the results. We are seeing that it has 0.07% of failures, which is not bad. It's very small. But when we look on the minimum, maximum, and average time request, it's quite stable. The whole application, even we were loading with K6 up to 100 users, at maximum there. Now that the latency is gone, you see just we dropped to 1 replica, everything is back again, but Carpenter is not sleeping. If you look up, he detects that he can run this whole thing in a cheaper instance, so he's draining nodes on the X large, and he thinks that with just a large instance, he's able to fit those replicas and those pods on the cluster. Huh? And we go. The fun stuff is that we're going from 0.18 cents an hour to 0.09, so we're already saving money. You might say, well, it's just a couple of cents, but when you do it at scale, believe me, there are millions that we can save. So we survived to this kind of storm that the app scale, Queda reacted, Carpenter adds more nodes there, but there's one thing. We were doing everything with x86 on demand. We usually hear if something works, why would you touch it, right? But if we stay there, we will not be able to keep trying testing and see if something can work even better there. What if we could get the same or better performance, but at lower cost, using less energy and making our infrastructure more sustainable? No? So we're going to go one step further. I'm just going to drop the replicas from the previous one, that was the Monte Carlo P, and now you will see when we get the deployments that there are 2 more Monte Carlo simulations from x86 and Graviton. And I'm going to run 17 replicas for each one and see how they are performing. We're going to look again back to throughput and latency side by side. Here is the 3 ones I was saying. I'll remove just the first one. So we just keep the 17 replicas that we want to do in our test. And once delete, put it, and we'll do again the same thing. The test is running, we'll check the logs, and we'll see how compare side by side. After this one is 5 minutes only, yeah? But again, we had to shorten to show things there. If we go, once we get it there, should have speed up the video. But you see now that it's publishing and doing Graviton and x86, the last 2 nodes that we have there. The other ones will be drained and disappear as Carpenter is working to optimize and see what's the best feature. This one has a trick because I don't want Carpenter to keep scaling because I want to reach the max out of the CPU. I want to put it on 100% to see how it really compares. Otherwise, if you put and it starts scaling, it's not the fun part. We want to really prove that this performs to each other. And you have the node pools for x86 and ARM that it will start showing. Again, we launch the test, and we put it in 2 different tabs that will see x86 and ARM. And once we execute, you will start seeing that suddenly at some point the CPU will start ramping up on both. We'll keep, one thing is on about instance, and I will tell it just a bit later. You see C8G, anything that is G, it's Graviton. The other ones are Intel, x86 in this case with AMD, but it's always 1 generation above. When you see C8, the equivalent on x86 is C7. And if it's 6, 5, and so forth and so on. You see now that CPU, we just hit 100% on each one. Things that looks like things are still keeping there, but we'll see in the logs if they just finish the test of loading the CPU and the memory. Memory just hits low, it will come 2% and maybe later like 20 after we're hitting the 100 virtual users on the side. And did it stop? It's still working and thinking. Look that we're already on $1,000 a month just by having the Graviton and the x86, but compare the price already, 0.6 against 0.7, bit more cheaper, same quality, but we don't even know if they have the same performance. And here comes when we think, people say, oh, it has the same performance, yeah, but you're paying less. So you have that trade-off also, but usually we'll find that you get better performance when running this whole thing. It came to 600 megs on that one. And let's check the test with the logs. You see, it must be 74, 75%. There it goes. All the tests completed, no interruptions so far. Same thing happens for Graviton. Another thing is what we are going to see when it finishes. The idea is that we're going to take both side by side, and rather than doing the math, that's another thing we usually find that you spend a lot of time comparing things and you build your script to, I need to check on the performance and stuff. I'm going to take this and I'm going to use an AI assistant. You might have Copilot, you might have other things that you usually do in your day-to-day. I'm going to use Amazon Q Developer that it's integrated in my IDE. You can do it both like a side and have your body on one side, or when you code directly, it can act actively, and we'll see it later. What I'm going to ask him is like, hey, help me do the math. I'm a bit lazy and I don't want to do all the computational things, but I want you to compare latency, throughput, cost, everything, what you got there. We put it in this one, the monthly cost that we were seeing on the price before, that was like 500 on one and 7 on the other one, just by default with the 2 nodes. But when we scale, we went to 1.7, as you really saw before. So now just picking the whole iteration that we had in the execution and dropping the performance test for each section, we will allow our AI assistant to make all the calculations for us. We usually try to say, don't hallucinate, just fix to this prompt that I'm putting there, and don't tell me anything that is not on that side. So we'll put on the Graviton, we'll click, and it will start thinking. It takes a few seconds to get it, and we did a workshop 2 days ago, and we were surprised that it did the transformation of a Python function to Java automatically, and it was not failing. It was like, ooh, things are getting better as we go over. And you see, it started getting me by section. But the whole thing is that it gives me, oh, you're paying 11% less, 60%, 3% more of throughput, 45 better latency, but 45 better price-performance ratio. So it's able to take your workloads, make it more efficient, make it cheaper, and it works the same. And even gives where it comes the links from or what he's checking on that side. So Graviton already gives us that better performance and lower cost. But remember, we are trying to maximize efficiency and make cost a true non-functional requirement. So could we go even farther? We talked about spot instance earlier, like business flight, just very, very cheap. What I'm going to do is I'm going to introduce that on my YAML. You will have, when I look on Graviton, so far they were on-demand, pay-as-you-go. We'll just change that to spot. And we were using the CAG family. The thing with Spot is that you need to diversify your instance so you get less probability of interruption. That's the trick of this whole thing. So I'll just remove it there. And then I'm going to take and look on the node class to see if it's already activated. That's where we define the type of instance that you can use. And you will see we just pick C, M, and R, all the different variants inside those instances. So it gives you a huge chance of getting less interruptions there. We just apply. And we're going to run again. And you see that suddenly it will just click. There's a Spot instance already being provisioned. It's almost automatically. Once you trigger and you recompile, you get the whole thing. And look now, from 0.68 to 0.25, now we're talking about big savings when you do it at scale and massively. It detects, it drains the node, it puts everything on that side, and you will see it down on the Graviton memory consumption. But not even CPU so far. This is a way of not moving to more efficient, but even saving more. And probably your CFO and your CTO will be happy with the results. So because cost is not an afterthought, it's a core decision, this takes us to the second law. And I will not bore you. There are only 7. Huh? So the second law is system that last align with infrastructure cost with business value. Here comes the thing. When we build distributed systems that they need to scale and operate globally and endure, you must ensure that the cost model scales with your business model. Don't spend more than what is coming, because then you will get into a huge, huge problem. And there's where we try to focus on the economic sustainability. And I'm going to put an example of one of our customers, a friend of Ryanair, who hasn't flown on Ryanair. They are the largest low-cost airline out there, and their business really depends on efficiency, automation, and very low margins. When I say low, you cannot imagine how low they are. Well, you almost pay for everything, right? But you can fly very cheap, and that's a cool thing that they have there. And the trick they're doing is they're using Spot instance in production, and they're heavily loading their data for reporting and analytics so far, and they have huge savings behind the scenes. Because a Spot allows them to save massively on compute while still meeting their operational goals. So it's kind of how we tie it, and I always try to say this. You need to try to tie your infrastructure to business KPIs. How you grow will depend on how good the company is working, and you will have a lot of constraints as things start growing, and those are the trade-offs we are always looking. We will never have that perfect solution, but you need to find how things can meet and satisfy all the teams. And not everybody will be happy when you take those decisions, to be honest. Huh? So this is not really an optimization. It's more an alignment that makes systems and companies resilient. Going to kind of the third law, wow, every decision we talk about trade-off, no? How many times when we try to optimize for cost, performance, or resilience, we are putting pressure on the other two? It's kind of a triangle in continuous tension. So what we're trying to do is to manage them with intention rather than sacrificing one. You heard at the beginning we said everything fails all the time, and yes, resiliency matters. But how much performance or cost are you, or cost efficiency, are you willing to give up for a little more uptime? It's like that classic word of, well, in Spanish, I don't know how to say it in English. It's kind of pick fast, cheap, and reliable. Pick two. If it's fast, cheap, maybe not reliable. If it's fast, reliable, it's not going to be cheap. So this is kind of that game we need to play here. So the real question will be, how do we find that sweet spot where our systems are fast enough, cost-aware, and resilient to handle all the chaos of the real-world applications that we have in our business? We just saw the Graviton, the theory says 40. We saw that it was even more on this side. But here comes the thing. If I'm moving to something that is a different architecture, is my application ready to run in ARM? That's the first thing. And there's a lot of fear from people saying, ooh, it's going to be a pain in the neck just thinking of moving these libraries, recompiling, and doing stuff. But mainly if you got that compiling Go, Rust, C++, and stuff like that, you need to really go on the whole thing. But if your stack depends on libraries, do we really have the availability to go? Because so far what I've told and I showed, we didn't change the code and anything, looks there. There are tools, and I'll show this one, that it's the open source one, that you just can go to the GitHub repo and upload. It's the Porting Advisor. It will scan your application, your library, and your dependency and give you an HTML report saying all the things that they will find in that application. Kind of blockers, bottlenecks that you might have. Maybe you're running a very old Java version, Java 8, and we'll say, oh, go to 17, and things like that. Or even libraries that are not compiled for ARM, and then you have a problem that you need to get back to your manager and say, this was nice, but it's going to take us 6 more months to do the whole thing. We always recommend this kind of tools that can give you a whole overview and really help you to really see how you can achieve your goals. But I detect, okay, there are things that I need to update, things that we need to recompile. But again, what about performance? And I show performance comparing instance, but we didn't go down to the CPU clock. And this is a short demo of doing that with LZ4. That is a compression algorithm. And I'm going to use a file from Dickens' site, that is the whole Charles Dickens library, put it there. So every time we see, and here are a couple of my instance on x86 and ARM for the Graviton demo. Let me go. So you'll see here the LZ4. You just can upload it down there. This is how we're going to warm up and decompress the whole thing. And I'll have kind of the first panel. On the left side is ARM architecture with Graviton. You will see it there based on Neoverse. And this one will be x86. On the middle is where I'm going to ask to just get the last 60 seconds of my CPU, and then we will compare just running this compression algorithm. Every time you see a number running on the top, once we build and it starts executing, it's 10 megs of file that it's compressing on that side. We do the same, just side to side you can compare. We are going to start doing the installation from FlameGraph. It's another tool that helps you watch on the CPU cycles. Very interesting with APerf. It's another tool if you want in the performance space. And if you see on the top, C5 large, that's x86 with G. That's the whole one. Single cycle, very small. Doesn't look so bad, 11%, 7 there. But if we go on x86, wow, it performs even better. It has to do more clock iterations to just do the same compression algorithm on that side. We just did on this next, it was like, okay, we were running this version. What happens if we update to the latest version of the LZ4 test? And you will see that performance is even better, because when you use the user usage, it comes from 96 and it suddenly drops to 93, 92. And on this one, it will be 96, 98 on the x86. It's very short milliseconds, but again, when you have millions of users, that are scaling a lot of savings you will have on that side. So our job as architects is to find the right balance for our system, knowing there's no perfect solution. Believe me, it's better just to throw out something and start iterating rather than trying to go with the best solution, because it can take you years or even months on that side. But there is a point where cost, performance, and resilience will align with the goals of your business. And again, I know I'm pushing a lot on this. Always be aligned with the business, because it's the only way to push your infrastructure forward. Huh? And that takes us to the fourth law. So far, we focus on compute decisions, Graviton for performance, Pod for savings, Carpenter for automation, and stuff like that. But there's something more fundamental. If your system is a black box, there's no optimization will ever be complete. It's like, and here comes the big problem, the hidden cost that you are not even aware of. I must have control of everything, but what happens if an external, and I show right now on this example, an external element has an impact in your design that you didn't even meant to design that for that, because it's something externally to you. Here we have for X-ray, but you can use Jagger, kind of have just a trace end-to-end tracing system with your microservices up there, that it helps me drill down and track to see where the problems is. And if you see, I'm getting some traffic, red alarms there coming from the main page we have, and the latencies are tracked. And we say our app is getting those spikes, and maybe it scales with Pod and do stuff, but nothing else happened. But when you zoom in and you realize that it's from an external API call from your front end, suddenly it's slowing down the whole application. And you didn't design for that. It's just a connection with a third party. Having this observability in place allows you to take decisions and proactively act behind the scenes to cover those kind of things. We always say, if you can measure, you can manage. So the most dangerous cost is the one you cannot see. And an observed system usually has these hidden expenses. I'm not sure if you have found something or someone can relate that. Hands up. Come on. You got into hidden cost? No, nobody else? Oh, don't be shy, huh? We all have gone over those things, huh? And this takes me to the fifth law. Because, okay, I know how much I'm expending, but I'm really controlling what I'm expending. That's the whole thing. Can I put proactive controls to take actions based on what's happening from a budget perspective? So Frugal architects don't just observe the cost, they implement these controls. You might have seen this tool like AWS Code Explorer that gives you the visibility, but you have the cost optimizer hub that gives you proactive suggestion like right size, move to a different architecture, stop, launch a new instance, which is kind of good. You still need to validate. At some point, AI will take over once it's really well trained, and we'll see doing those actions for us. But there are also things that if you ever wonder how much you could save by moving to Graviton in this case, this is an open source project also, that you just can download, install it in your account, and it will give you the realized savings that you had compared to different architectures. How you amortize the cost is going to show even by instance type. So you can really drill down on all the specifics and have a clear view when you go into those conversations with your stakeholders. Huh? Here it shows for a specific account, type of instance M6G currently using, how much is the consumption on that side. And this is the kind of thing that we usually try to take, that you break down and what are the next 6K savings that we can have in our architecture. It works, but we are looking to make it more efficient and maximize that efficiency. So we design things with these control points, and because the real optimization happens where cost efficiency and user experience. I know I'm talking a lot about how we optimize and cost, but here the main thing is how my user has that sweet experience when navigating in our services and using our applications. And that takes me to the sixth law. We're almost there. Optimization isn't just a one-time event. It's a mindset. Even if things are working, you need to still check the defaults, see how you can run. Maybe a few milliseconds doesn't mean anything. At scale, I always say thousands of savings. So every micro-optimization adds up, especially in distributed system. And I'm going to put here an example of a Python code that I wrote, and I asked the AI to make it more efficient for me. And we run like 4 tests for the basket case of my shopping cart. and it will come and say to check the discount if it's 50%, 100%, there's no discount to ensure that there's no wrong numbers when we build, because that's another issue. If you get, oh, there was 0% cost and I can buy for free things, we see it some retail happening. Once I do the test and there's no item in the action, it makes the good thing, no discount applies, and it gives you what's the actual thing. That's my original function. And now I have AI that I say, optimize. Oh, he already provides some code. And I'll say, okay, I think mine was more optimized because he went into a loop. I'm going to run a performance test between both functions and see how fast is one compared to the other, doing 10,000K iterations for each function. So when I run the first time, you see 0.03. With my original, the optimize is even faster. And even it comes 0.001 faster compared on the other one, that again, at scale, that's thousands of savings. So we're not optimizing just the infrastructure, we're also optimizing our code. And this needs to be a stack that comes complete and cross on that side. I ask, again, Q developer, like, hey, give me, because I'm not understanding why he comes with a loop that should be less optimized than my function, and he's getting it higher speed. And he comes with an answer, and it was like, okay, I need to update my programming skills for this, huh? So there it goes. So small changes today can be big savings tomorrow, and these improvements today can snowball the whole thing that you can go. And this takes me to the last one, that our x86 work, it scaled, it passed the test, but if we stop there, we would just miss the cost savings or the opportunity to make it everything more efficient. Frugal architects don't settle down for good enough. They always look for something else, no? We usually say the curiosity killed the cat. It doesn't work in this world. You need to be really curious on how you can improve things and work. Don't do it in production. Just tested before. But the thing that what worked yesterday may not be enough today. So we always question the false test alternatives, welcome changes from XCC to Graviton, from static capacity to dynamic with Spot, from it runs to it runs better. So it's not just being frugal, it's evolving the whole thing. If I had known these 7 laws when I was young, I probably have written less post-mortem and slept more in my early days. So each law is a reminder that building system is not about chasing perfection, it's about making smart trade-off. And in a chaotic world, frugality isn't a constraint, it's a superpower. And you don't have to wait until you get old to just start applying. There's a QR code where you can see more on Werner Vogels laws. He's updating and he's expanding this whole thing and bringing customers to tell their story. So I really suggest to look at. And that's all for my session today. Thanks very much. Huh?